Good evening and welcome to everyone. My name is Alex Lupsaska and I'm a theoretical physicist here at Harvard studying black holes. And as a black hole physicist, I have been eagerly awaiting the first real image of a black hole in the sky for many years. And I think I speak not just for myself, but for many of us when I say that this last week, which saw the release by the Event Horizon Telescope of the first actual picture of a black hole in our sky, it's really been a dream come true. And so it's a great pleasure and honor to introduce our speaker tonight, Dr. Michael Johnson, who is a key member of the Event Horizon Telescope collaboration, and will tell us how this incredible image was taken. So a few words about Michael. He's currently an astrophysicist at the Harvard Smithsonian Center for Astrophysics and a crucial member of the Event Horizon Telescope team. Before joining us here, he studied physics and mathematics at the University of Southern California and then received his PhD from UCSB in physics, where he studied pulsars and interstellar scattering. He initially joined the Event Horizon Telescope team as a postdoctoral fellow in 2013 and has since become a leader of the EHT Imaging Working Group, which is directly responsible for reconstructing the beautiful images of black holes that we've been looking at this last week. And let me mention only his most recent prize. He was awarded last year the Secretary's Research Award from the Smithsonian for his pioneering work developing new algorithms for dynamical imaging, which should eventually allow the Event Horizon Telescope to reconstruct entire movies of black holes from the data it collects. Michael contributes broadly across the EHT project beyond imaging methods. And in particular, I think it's important to mention his remarkable generosity towards his younger colleagues. He advises and mentors several students. And in fact, I myself came to know him when I was a graduate student, and he very graciously took the time to explain the basics of how the Event Horizon Telescope works to me, which I'm still grateful for. And his explanations have always been clear and illuminating, so I'm sure that we're in for a real treat tonight. So without further ado, please join me in welcoming Michael Johnson.
First, can you hear me okay? Yes, okay. Thank you so much, Alex, for the gracious introduction, and thank you all for coming. I'm just so delighted to be able to share with you these first results from the Event Horizon Telescope. Now, this is a project that took decades to complete and involved hundreds of people, but many of the crucial contributors actually work here in Cambridge. So I'd like to give you a sense of how this project came to be, what our first results are, and what they mean for astronomy and physics. So if you go out and you look up at the night sky, tucked in between the constellations of Leo and Virgo is the giant galaxy M87. Now, M87 is enormous, but it's also 55 million light years away. And what this means is that even with the best optical telescopes in the world, or even with the Hubble Space Telescope, all you see is a little ball of stars and a faint jet extending from them. If you use... Sure. Is it possible to lower the lights? Oh, we'll do it in a minute. So peering all the way down, you can use radio techniques to get all the way down to the core until you finally end all the way at the base of the jet. So this is the first image with the Event Horizon Telescope. And you can see it required two things. It required pushing to higher angular resolution than ever achieved before, but it also required pushing to high frequencies so that you could see the jet become translucent and go all the way to the center. Now, what we're seeing here, maybe we can keep the lights a little lower in the front. I'm not sure who's. And we're back. Okay, maybe somewhere in between bedtime story and. Well, okay. This is like my experience with Alexa. It's like, Alexa, just the front lights. Like, no. Anyway, I assume someone is fiddling with this in a healthy way. So what we're seeing here is actually pretty simple. We're seeing an incredibly large black hole that's in a bath of hot glowing plasma. And this plasma is heated to tens or even hundreds of billions of degrees. And this black hole is an absolute monster, okay? It's about 7 billion times the mass of the sun. Okay, so we have many ways of inferring that there might be black holes in the universe. You can see how they affect the motion of stars and gas. This is one of the biggest black holes inferred by any method anywhere in the universe. It is huge. And so to give you a sense of that, if the Earth were compressed down to a small enough size that it became a black hole, so you condense all of its mass into a small enough region that not even light can escape, it would be about an inch across. You could hold it on your finger. For comparison, the event horizon in M87 would engulf our entire solar system. It would extend beyond the orbit of Pluto. It is huge. But one interesting thing is that bigger black holes are actually less dense, the average density within their event horizons. So while this Earth sitting on your finger would have just unimaginable density, the black hole in M87 actually has less density than the air that we're breathing. It's about the same as the air on the top of Mount Everest. So black holes are really quite fascinating. So the real game here is that even though this black hole is enormous, because it's so far away, it's got this tiny angular size on the sky. This image is about the same angular size as if you put a donut and stuck it on the moon. It's also about the same angular size as holding an atom at arm's length. So the game is, how can we create a telescope that can see things that are this small? And to do that, we need to think of a new type of telescope called an interferometer. And to understand how an interferometer works, it's helpful to draw some inspiration from ducks. So here we have some ducks. They run, they jump into a pond, and they start kicking their feet wildly, okay? So there's this little cluster of ducks. They're kicking away, and they're stirring up the water near them. It's stirred up and turbulent. But if you look further away from the ducks, what you see are these nice outward propagating wave fronts far away from them. So close to the ducks, it's nice and stirred up. Far away, nice smooth outward propagating wave fronts. So I'd like to pose a puzzle to you. Suppose that you're standing on the edge of the pond, and you want to tell where the ducks are in the pond. But the trick is we'll say that you can't see them and you can't hear them. You're blindfolded and your ears are covered. So all you can do is you can stand there and you can feel the water lapping up against your feet. And how do you use that information to tell where the ducks are located? Okay, so let's unpack this a little bit. Here, we'll do two simple toy models. On the left, we have ducks that are clustered close together. On the right, they're spread far apart. So let's let the ones close together start splashing. They're kicking up. It's nice and turbulent and irregular in the center. And far from the center, you see these outward propagating wave fronts. And just imagine that you're sitting there on the edge of the pond, feeling the water lap up and down. Okay, now let's let the other ducks go. So now these ducks that are further spread apart on the right, we're going to let them start kicking and splashing. Same thing. In the center, it's nice and turbulent. Further apart, you see these outward propagating wave fronts, and you're standing on the edge of the pond, and you see that water lapping up and down, just like in the left case. And you'll notice that there's a pretty big difference between these two cases. And that's that they have very different coherence lengths. So if you're just standing by yourself on the edge of the pond, these two cases would look the same to you. You see the same amplitude of fluctuations of the water. But let's say that you have a partner who's standing a little ways away from you, and you can compare the water that's lapping against your 2 feet. Now, if you're standing very close to each other, what you see is that you experience about the same pattern of sloshing. And as you move further and further apart, at some point you'll see different patterns of sloshing against your feet. And it turns out that if the ducks are very tightly packed together, then you and your partner can be very far apart and still see the same sloshing pattern. But if the ducks are spread far apart, then you and your partner have to be close to each other. So let's just let them play at the same time, and you'll see this. Again, just imagine you and a friend are standing on the edge of the pond, and you're comparing that sloshing pattern at the same time. So what this is telling us is that the correlation structure around the edge of the pond is actually the thing that contains all of the information about where those ducks are located. And actually, it's a very beautiful relationship. It's a Fourier relationship between the distribution of the ducks in the center of the pond and the splashing pattern that you see on the edge. Now, I know this seems whimsical and probably irrelevant, but it's actually almost a perfect analogy for what we're doing with the Event Horizon Telescope. So for a black hole, we don't have ducks, but we do have electrons. And these electrons are gyrating around magnetic fields. And as they're gyrating around magnetic fields, they're sending out ripples of electromagnetic waves, just like the ducks in the pond. And of course, the distribution of electrons, or the image on the sky, that's like the distribution of ducks around the pond. So we have this black hole that's sending out these electromagnetic ripples, and so we take telescopes and we spread them apart as wide as we can. And then we compare the electromagnetic waves that are being received at each of those telescopes. And the correlations of those waves tell us what the distribution of the image is. Okay, if you just have one telescope, all you can tell is how many electrons are gyrating at all. All you can tell is sort of how much total emission there is from the object. But if you piece them all together and act like an interferometer, this is like you and your friend being spaced at different distances, then you can tell how the emission is actually distributed on the sky. And this technique is called aperture synthesis. So you're synthesizing an aperture. And this was pioneered by Martin Ryle, who actually won the first Nobel Prize in astronomy for it. So why would we go to all this trouble, though? What's the advantage? So for ordinary imaging, it turns out it's pretty easy to tell how fine of details you can resolve. It just depends on two things: the size of your telescope and the wavelength of light you're using. So this is something called the diffraction limit. You just take the wavelength divided by the size of your telescope. So for the human eye, observing at visible wavelengths, it turns out that the resolution that you can see is about an arc minute. Now, radio telescopes can be enormous. They can be hundreds of meters across. But it turns out that the wavelengths of radio telescopes are so much longer that even big radio telescopes have about the same angular resolution as your eye. They're not great for angular resolution. However, optical telescopes can, of course, be much larger. They can be meters across and observe at the same wavelengths as your eye, so they can see thousands of times smaller details. Now, what about interferometry? So the magic of interferometry is that your resolution doesn't depend on how big you can make any one telescope. It just depends how far apart you can put them. So instead of lambda over the size of the telescope, it's lambda over the longest baseline you have, the longest separation between a pair of telescopes. But this comes with a price. Interferometers don't produce an image like a CCD does. They don't just spit out an image. And instead, each baseline, each pair of telescopes is just sampling one spatial frequency of your image. So one way to think of this is, you can imagine if the image were a song, then each baseline in your interferometer would just hear one note of that song. So if you want to see the whole image or hear the whole song, what you need is many different baselines, both long and short, and you piece all that information together, and that's how you get your image. So I want to give you a sense of what this is like for an interferometer. So we're going to do a demo where it's as though you are an interferometer, okay? And so I'm going to take a song, and I'm going to sample it as though you only have a few stations listening to it. So if you have two sites right at the beginning, you're only going to hear one note of that song. And we're going to slowly add more and more sites, and more notes of this song will come into view. Okay, so what I'd like you to do is when you recognize the song or you think that you hear most of the notes, go ahead and raise your hand. So here we go. So there's 4 stations and 6 notes that you hear right now. Yeah, a few people. So that's how interferometry works. Now, the beautiful thing that you might have noticed here is that you can be missing a huge amount of information and still be able to tell what the song is playing. And this is the idea of interferometry. Maybe we don't have to make a telescope as big as the Earth. Maybe we just sparsely put telescopes all over it, and then somehow we can fill in that missing information with algorithms. So that's the idea of the Event Horizon Telescope. The EHT isn't one telescope, it's a collection of them spread all over the Earth, all the way from the South Pole to Greenland. And acting together, these telescopes achieve an angular resolution of about 20 microarc seconds. So this is more than 1,000 times better than the Hubble Space Telescope. Now, we didn't build these telescopes. That's part of the key to the success of the EHT. What we did is we took existing sub-millimeter telescopes and we added atomic clocks to them so they could be perfectly synchronized and to act together as an interferometric array. The other thing we did is that we added high-speed recording equipment. So for us, if we swallow more data, that's like making our instrument more sensitive. That's like building bigger telescopes. And so we're latched onto Moore's law, and currently we're recording data at about 8 gigabytes per second at every telescope in the array. And so we're able to turn these massive amounts of data into an incredibly sensitive telescope, and that's how we're able to push into regimes that were never accessible before. So when complete, you can see that this angular resolution of the EHT is smaller than the size of the black hole shadow that we saw in M87. And you see this big blurry puffy image, and that's because we're really pushing our instrument right to its limit. We don't think that it's actually a blurry image on the sky. That's as fine of details as our instrument can see. But I just want to, we've discussed some of the absurdity of the EHT, but I just want to give you one more handle on it, and that's that you can imagine, suppose that the EHT points at M87 and just recorded continuously for a year. The total energy it receives from M87 would be less than the energy released when you pop a soap bubble. It's just absolutely stunning that we're able to turn this into pictures of black holes. It's this incredible achievement of humanity. Okay, so from start to finish, the EHT is all these telescopes. Each of them has these recorders, and so they're recording the incoming electric field. Now, that's recorded onto disks, huge banks of disks, and so these are actually taken on airplanes to single centers that then combine all of that data and basically turn it into a digital telescope. They add delays, and that's like it's like unfolding the Earth into a parabolic mirror. Okay, and you can actually digitally point your telescope as well. Then we correlate, we calibrate, and we hand it off to imaging, and then we have algorithms that try to turn that data into these images. Okay? The extraordinary thing here is that our recorded data is these vast amounts, petabytes of data. So if you, in terms of hard disks, it's about half a ton of hard disks to record the EHT campaign. However, once we're done doing all of this processing, we actually collapse all of that down with no loss of information. And so the final data products are something like a megabyte. They can be emailed. Incidentally, this is one of the reasons we were pretty worried about leaks before the announcement, because it's pretty easy to inadvertently just send off the entirety of an EHT observing run. But one other nice aspect of this is you can actually go online, you can download all the data, and you can get your hands dirty with it yourself. And all of our data and our imaging algorithms are available online. So this is something that's really worth a shot if anyone knows Python. Okay, now something you might be wondering is that in 2017, the EHT only had actually 5 sites that could see M87. And that means it only hears 10 notes. And even in that simple case of the song, most people, I think no one could recognize it with only 10 notes. So the question is, how could we possibly turn only 10 notes into an image? What are we missing? So it turns out we have one more trick to play, and that's that we make the Earth part of our instrument. Okay, so each baseline is joining a pair of telescopes, but all we care about is the projected baseline as seen from the source. So here on the left, we have the Earth. That's one baseline joining our sites in Chile and in Spain. And then that translates to one particular frequency measurement. But as the Earth rotates, those fixed pair of sites sample different frequencies. And so as the Earth is rotating, it's actually sampling lots of different frequencies, even for a fixed pair of sites. And so over the course of the night, we can gather together lots of information, and then we can take all of that cumulative information and turn it into just one picture. So this is a concept called Earth rotation synthesis. We use the rotation of the Earth to fill in more of this missing information. And that's a critical part of the success of the EHT. Okay, so now we have to take this data, we have to turn it into a picture. In practice, this took us about a year. Why is it difficult? So I want to take you back a year ago and just try to put yourselves in the position of what we were doing. We're trying to take a picture of something that no one has ever seen. We're trying to do this using only a handful of measurements that are very difficult to calibrate. And we're trying to do this with an instrument that no one's ever used before. Okay? And it's even worse than you think. So this technique of very long baseline interferometry has never been used to make an image of anything ever at 1.3 millimeters. We can't point at anything on the sky and say, okay, we think our instrument's working because we got what they got, or we got what we got last year, or something like that. Everything we see, we're seeing for the first time. And so there's this terror. What if something in our instrument is broken, and that's causing us to see something that's not actually legitimate? And to make it even, so this image of our frequency coverage, the points there, that's where we have measurements. And the white is this desert of unknown. That is everything we don't know. So we're trying to take this tiny amount of information and turn it into a picture. And it turns out that there are an infinite number of pictures that are perfectly consistent with all of your measurements. And so we have to be extremely careful that nothing we're doing at any stage of the data collection or the data processing or the imaging is biasing our results. So how did we do that? So the first thing that we wanted to do is we wanted to start off and make sure that we're being absolutely honest with ourselves. People are very good at rationalizing things after the fact. But what we wanted to do is to eliminate the possibility for that. So we started with blind imaging. So we took our group of the imaging team, which was about 40 people, and we divided up into 4 different teams. And the day that the M87 data were released, we ceased all communication between the teams. So each team got to go off and analyze it in their own way. They got to use their own imaging algorithms, their own imaging software, and they were charged with making an image. Now, it's not just the imaging that's difficult in this. In interferometry, often the data have to be discarded. So for instance, some telescopes have trouble tracking the source at particular elevations. So it might be that sometimes you get data that's just garbage and you have to throw it away. Or it might be that sometimes in the morning when the sun comes up, there are thermal deformations on the telescope that cause a huge loss of sensitivity from lack of focus. And so you have to make these judgments about, like, I think, maybe one team will say, I think this data is garbage. I think this whole telescope's data is garbage. We're going to throw that away. But another team might say, no, we think that's fine. And another team might say, well, we think we can calibrate that. And so every team is making their own decisions, and there was no communication at all. So each team worked for 7 weeks. Then we all came together at a workshop just up the road, and we unveiled, for the first time, what the images from each team were. And this is what we saw. So these were the first images ever produced of M87 from these 4 different teams. And what I love about this is that they're not the same. Right? This gives you a sense of the things you can believe in the image, but it also gives you a sense that there's quite a bit of uncertainty in other aspects. So every team saw a ring. Every team saw a ring that was bright in the south. And every team saw a ring that was about the same size. Beyond that, pretty much everything is uncertain. One team sees something that looks like a jet going off to one direction. There's different depths in the center of the ring. There are different thicknesses of the ring. And so you begin to understand this challenge, right, that our instrument doesn't deliver an image. Our instrument delivers data, and then we have this infinite space of images that we need to explore, and we need to understand what's possible and what's not. And we have to understand how that translates to uncertainties about the physical quantities that we're studying using the images. So here's an image of the group at the first imaging workshop. This is just after we had compared for the first time. We're all seeing this for the first time. And I think it's pretty clear we're pretty happy. This is we had done lots of tests. And in tests on synthetic data, there are lots of cases where maybe you produce a ring and you're very confident, and then someone else takes the same data and they produce a big booming jet or something like that. So this was really the moment when we thought, we have it. We know that this is the image. I just want to point out a couple of the key contributors here. So Andrew Shale up here up top, as part of his thesis work at Harvard, he's a PhD student, developed an entire new imaging library for VLBI. This is all open source. You can download it yourself, and he just did a spectacular job. He built this from scratch on his own initiative. Kazuo Akiyama is a postdoc at MIT Haystack, he also developed his own imaging library from scratch just for the EHT. Katie Bowman, who some of you may recognize, is another absolutely foundational contributor to these efforts. She was a graduate student at MIT CSAIL when she first joined our team in computer vision. And so she brought this whole new testing framework, testing on thousands of sets of synthetic data and really developing an entirely new prescription for how we understand uncertainties in images. So we had this core group of people that was kind of building these things from the ground up. And in our final results, we actually published 3 different pipelines. So one of them was this classic VLBI software that's been used for decades, and the other 2 were developed by graduate students. And I think this is just an amazing contribution from junior members. In addition to them, there are lots of other local contributors, maybe some familiar faces in here. Some really talented students and postdocs. We also have the director of the EHT is Shep Doleman, who's at the Center for Astrophysics. And along the way, we picked up a few stragglers. So Peter Gallison is faculty at Harvard in philosophy and history of science. And Peter, I think, came along just expecting to do some filming, but he got pulled into it. And at this workshop, he's got his sleeves rolled up, he's got his laptop out, and he was imaging with the rest of us. And he brought a huge number of ideas to the imaging team about how we understand rigor and how to develop certainty in images. And Ramesh Narayan is an astrophysical theorist who actually got his start in imaging back in the 80s. So a lot of the algorithms that we're using were developed by him, 30 years ago. So a lot of locals got involved, and it was just a lot of fun. Okay, so we had these images. We're feeling pretty confident that we believe them. What do we do next? You can't just pick one and say we like this one best. How do we go from a few images that we think are broadly consistent to, say, a final image or something that we're ready to interpret for science? So for that, what we wanted to do is develop a new objective method for selecting which imaging algorithms were best. And so we developed suites of synthetic data. And our procedure was basically, we took these different geometrical models. So here you can see a ring and a crescent and a disk and a double. And these were selected so that when you create synthetic data sets from them, they look a lot like the M87 data. So we would create these synthetic data sets, we would sample them as though the EHT was observing these things on the sky, and then we pass them through our imaging algorithms without telling them that these aren't real data. We just process them in exactly the same way. So on that bottom row is one imaging procedure that's used identically across all 4 of these. And the terror that we were trying to address here is maybe you produce an imaging algorithm, it works really well on rings. It produces beautiful rings. Maybe they're so good at making rings that it even makes rings when you give it a disk, right? Or likewise, maybe something's very good at disks or point sources, but it breaks down and doesn't produce rings when there's one in the sky. So we wanted to test, are we overtraining our algorithms, or are they really reliable enough that they can show us things that we weren't even expecting to see? And so that's what this was really all about. The other part of this is that because we know the ground truth image here, we can objectively say this algorithm works better than that one, or this particular set of knobs that I can turn for each algorithm is better than that. And so we use this to generate hundreds of thousands of imaging parameters, and then to select spaces among them that produced good images for all of these training sets. Now, I just want to give you a sense of this process of image formation and kind of how it's using the data to make a picture. So here, I filtered the data. This is actually M87 data, but I'm filtering it so you just get one baseline. Now, when you have just one baseline, you basically only know one mode in your image, so it's just enough to tell you kind of how big the image is. So you can see that on the right there, that's our final imaging scripts, just using this data, and all it produces is basically a big blob on the sky. Okay, now we'll add a second baseline. The second baseline now gives us now we have 2 modes along the same direction. And so it actually tells us there has to be a little more power there, so it breaks that blob in half, and you see this double now. We can add a 4th site. Now we have 6 baselines, and you start to see this ring structure emerge. And you see that the ring has the most structure along the direction of the baselines that you have. And then finally, when we add our last station in Spain, we get good resolution along all directions, and that ring sharpens up, and we get to our final image. So at this point, we had a pretty good handle on, we think the ring is there, we think we understand our data, but the thing that really clinched it, I think the reason that we're not holding our breath is that we have 4 different nights of observations. So each night is different. Each night has a different observing cadence. Some nights had a lot of time observing M87. Some only had a few scans observing M87. Some nights, maybe the telescope performed well, others poorly. Some nights had good weather, others had poor weather. It's a really nice way to just check and make sure that everything's consistent. And here's the 4 images of M87 across the 4 nights. And they're just so beautifully consistent. Now, you will notice some changes, and this is part of the excitement. The 2 days, April 5th and 6th, look very similar, and April 10th and 11th look very similar. The 5th and 6th have a little more flux up sitting on the left of the ring, and on the 10th and 11th, there's a little more on the bottom. And so this is actually intrinsic variability of the source. And the reason we know this is that we see it in raw data. You can actually see it in particular data combinations called closure quantities that are independent of calibration. And so what we see is that the source is actually evolving before our eyes. It's not just some dormant black hole that's sitting and doing nothing. It's living, and we're starting to see that evolution of the black hole. Okay, so what does this mean for general relativity? How do we interpret this image? Yeah, as my daughter explains, black holes are orange. So, yeah. So this is actually fairly fascinating. So what we see is broadband emission from M87. There's no color information. We just see brightness as a function of position. So this is entirely artificial color. We spent a lot of months iterating on exactly how to visualize it. You want to develop visualizations that don't draw your eye to particular features that are just the choice of the color, the sort of the way in which you've colored it. So this is something called a perceptually uniform color map. I think there are entire people who devote their lives to studying these things. But yeah, the color means absolutely nothing beyond the absolute intensity at that position. Yeah. Okay, so near a black hole, the gravity is so strong that even light is bent. So these are photon trajectories near a black hole. And you can see that if photons come close to a black hole, they can get whipped around. They can even get trapped on orbits around the black hole. And the net effect of that is if a black hole is sitting in a bath of hot plasma, it'll cast a shadow on that background, and that shadow is almost perfectly circular. So what this shadow is encoding is the properties of the space-time near the event horizon of the black hole. Okay, so we can use this to see whether or not general relativity is correct. Okay, so to start off, imagine that we have a non-spinning black hole. This is called a Schwarzschild black hole. And the reason it's called that is because Einstein published his theory of general relativity in 1915. And Karl Schwarzschild was a theorist who actually derived the first non-trivial solution in general relativity. And he did this during World War I. He was actually in the trenches at the time, and he died less than a year later. But it was this incredible achievement. And less than a year after that, David Hilbert, a mathematician, was the first to calculate the diameter of this Schwarzschild black hole. He's the one who calculated it should be 5.2 times this gravitational radius. But I love this quote by Schwarzschild in a letter that he wrote to Einstein. He says, as you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas. So really, incredible what people can do even amid incredible adversity. So that's the shadow diameter that we expect if there's a big black hole and it's not moving at all. Now, after Schwarzschild, there was sort of a long lull until the 60s when Roy Kerr derived an exact solution for a spinning black hole. Okay, so it might be that there's a big black hole, but it's actually got angular momentum. And in that case, the shadow becomes just a little bit smaller. Okay, and this is something that was calculated by Bardeen in the 70s. And Bardeen, in his paper, has this nice quote: "It is conceptually interesting, if not astrophysically very important, to calculate the precise apparent shape of the black hole. Unfortunately, there seems to be no hope of observing this effect." So, I mean, this is not so long ago that this was thought to be impossible. So you can see the space between a non-spinning black hole and a maximally spinning black hole, and that's actually the full space of possibilities if general relativity is correct. Okay, that's the only range of possibilities. You have no other knobs to turn. Okay, so this is something called the no-hair theorem for black holes, that a black hole is described entirely by its mass and its spin. And this is very fundamental to general relativity. And I love this quote from the famous theorist Chandrasekhar. He says, "In my entire scientific life, the most shattering experience has been the realization that the exact solution of Einstein's equations of general relativity provides the absolutely exact representation of untold numbers of massive black holes that populate the universe." So we want to test this, right? We want to see, are black holes really described entirely by their mass and spin, or do they have hair? Okay? Now, the problem with M87 is that to do this, you have to know the mass of the black hole ahead of time. The size of the shadow is proportional to its mass. So these shadows that I'm showing you correspond to mass estimates that we get from stars that are zipping around M87 on large scales. But you can also estimate the mass of M87 using gas. And in that case, you estimate that it's only about half as big. So the gas estimates of M87 said that it has about 3.5 billion solar masses. The stellar estimates of M87 said it had about 6.6 billion solar masses. So if we knew it was one or the other, then we have a precise test, but as it stands, all we know is that it's somewhere in this range. Okay, well, what if it's not a black hole? Well, just for fun, maybe it's a wormhole. So it turns out people have predicted what the shadows of wormholes would look like, and they're different than black holes. It turns out they're about half as big. So if you take the stellar estimate of the black hole mass and you apply it to a wormhole, it'd be about the same size as this smaller gas estimate of the black hole. And we don't have to stop there. Maybe there's a singularity at the base of M87, but it's not shrouded by an event horizon. So maybe there's a naked singularity that lives there. This is also a valid solution to Einstein's equations, but people don't think that it exists. Nevertheless, it would actually cast a different shadow. So here's the shadow we would expect if it was a naked singularity, smaller yet. So we can put our image on top of these, and all of a sudden we rule out all of these possibilities except for one. So this estimate of the mass from the gas, it doesn't all have to live in the black hole. It could be on bigger scales. So the gas estimate could have been consistent with anything equal to or smaller than the ring that you saw. So we can rule that out now. We know that there's something flawed in that method. The naked singularity and the wormhole are the same. They could have been smaller than these estimates, but it can't possibly be larger, so we can rule those out. And what we're left with is that the black hole that we see is perfectly consistent with canonical general relativity. There's no indications of departures from sort of garden variety GR. Now, looking at this image, you might be mistaken and think that this is kind of a sleeping giant, but we actually have numerical simulations of what black holes look like, and we expect that this thing is going to be tremendously dynamic. So here is a three-dimensional simulation, one of our best simulations of M87, and you can see that this thing it's not sleeping at all. This is a swirling cauldron of fire. Right? 1 second in this simulation corresponds to 2 weeks in real time. So this is actually an opportunity to watch black holes evolve, to see them live and breathe, to see material fall through the horizon or be ejected into the jet. This is an entirely new way to study black holes. The question is, do we see any hints of that? Is this little bit of variation that we see over our 5-day window or 6-day window, is that this variability? If we could look at it with sharper resolution, would we see this? And I think something really exciting is that we already see hints of this on larger scales. So at slightly longer wavelengths, the jet has not become translucent. You still see it. So this is one of the highest resolution images that was ever made of M87 before the Event Horizon Telescope. And this is at 7 millimeters. Okay, so here you're not actually seeing all the way to the heart of the jet, and so you see this big booming thing that actually extends for tens of thousands of light years. And what we can do is we can take observations of this jet over many months, and we can stitch them together. And instead of reconstructing just an image, we construct movies. And so here we go. This is the jet of M87. And you can see, indeed, it's alive, it's breathing, it's writhing, it's ejecting material and power out to extreme distances. And the incredible thing now is that we know that that's being powered by this black hole that's sitting right at the heart of this system, this tiny little spot at the heart of the jet. One of the most exciting things to me about our results, and this is something that's still tentative, it's something we have evidence for, but we don't have conclusive evidence for it, is that it appears that the jet is actually being powered by the black hole. Okay, so people often talk about black holes liberating gravitational energy. So they pull material in and it gets hotter and it glows and it releases energy. But it's actually possible to extract energy from the black hole itself. And this seems incredibly paradoxical. You know, once you fall into a black hole, aren't you done? How do you get energy out of that? But it turns out that if a black hole is spinning, it's possible to slow it down. Now, a spinning black hole with the mass of M87 could have enough energy to power 1 billion stars for the age of the universe. A spinning black hole can be incredibly efficient, and this is how it works. You have magnetic fields that come through, they pierce the event horizon, and as the black hole spins, the magnetic fields get dragged along with them, and that's like wires. So this is like a motor that is spinning up these wires, and it's generating currents above and below the black hole. And so we think that this could happen in nature, and in all of the simulations that we have currently that are consistent with the Event Horizon Telescope observations and that are also consistent with the jet power we see in X-rays, these are all indicating that the black hole is actually powering that jet through its spin. So if we can somehow connect this variability all the way down to Event Horizon Telescope scales, then we might be able to see this living black hole that's actually the source of the power in the jet. Now, looking at this image, you can quickly forget, again, that this is an enormous black hole. And, well, I was talking to Jim the other day, and he said, you know, if the black hole is a foot, and the size of the galaxy is the size of the United States, it's, you know, the black hole is just some tiny speck at the middle of this vast system. But just to use a fictional example to reinforce a point, the black hole that we now have seen in M87 is actually 70 times bigger than the fictional black hole Gargantua in Interstellar. So, for what that's worth. Let me just close by reiterating again that the Event Horizon Telescope is a huge collaboration. We currently have over 200 members, and there have been more who contributed along the way. These include engineers, computer scientists, mathematicians, astronomers, physicists, and more. It's been a huge group effort, such an honor to be part of it, and I'm so delighted to be able to share it with you today. So thank you.
This black hole is so far away, how do we know it still exists? Because it's like huge.
That's right. So the picture we're seeing of this black hole, and I guess we have some mics here. If, put Alex to work. So M87 is 55 million light years away, so we're seeing a picture that's 55 million light years old. Things on those scales can't evolve too fast. So it would be hard for the black hole couldn't just disappear. The only thing that could really kick it far out of a galaxy would be maybe a merger or something like that, and those are very slow. So it's unlikely that it's just speculation, but there's not much we can say about it today, of course. Yeah.
Why do we have telescopes in Asia and the Middle East? The other telescopes are in Europe and Americas, but not in Asia or Middle East. Why?
Yeah, so there are East Asia networks of telescopes. They don't observe at 1.3 millimeters yet. So it's this incredible thing, right? Imagine you're a photon in M87. You have to travel tens of thousands of years just to get out of the galaxy of M87. Then you have to travel for 55 million years to make it to us. Then you have to travel for a few tens of thousands more to make it through the interstellar medium of the Milky Way. And then you get swallowed by our atmosphere, right? So the thing that kills these things is water vapor in the Earth's atmosphere. And that's why our telescopes are located at these crazy locations. I mean, we like to travel, but not that much. We have telescopes right in the South Pole because the air is very dry there. The telescope in Mexico is at about 15,000 feet. There are very few sites on Earth that are good enough to be able to observe even a fraction of the time at these wavelengths. It's really tough.
Why isn't it symmetric?
Yeah, do you mean why is it brighter on the bottom, or why isn't it perfectly circular?
Why is it brighter on the bottom?
Okay, yeah. So there's a relativistic effect that if I'm holding a light and I'm moving very fast, people in front of me will see it as brighter, and people behind me see it as fainter. So this is a relativistic Doppler effect, like an ambulance coming towards you or moving away. So what we think is going on here is that material around the black hole is going really fast when it's this close to the event horizon, swirling around it at close to the speed of light. And what we think is that the jet's pointed almost at us, and it's moving clockwise. And the stuff on the bottom is coming towards us, stuff on top is moving away, and that's why we see it brighter on the bottom. Yeah.
Thank you. This is so exciting. It's
Thank you.
wonderful talk. I think, well, there's been something that's bothered me since the picture was released, and I think the answer might have been actually hidden in the slide that showed the photons whipping around the black hole. But I haven't understood why there is a black center. Like, it's in 3 dimensions, so why isn't it orange all over or yellow all over from where we're seeing it? Like, what makes the black hole in the center?
Yeah, that's a great question. You're absolutely right. So, and it's a little confusing from these images. We actually think that the jet in M87 is pointed almost straight at us, okay? And it just is going off at an angle because, that's a projection effect. But this thing is pointed almost straight at us, and so there's all sorts of stuff that's in front of the black hole that's glowing, right? And so these images of the black hole, it's not perfectly black in the middle. There is stuff there. And if we can make higher and higher dynamic range images, we will eventually see not just this ring, but we'll also see it connect to the black hole. We'll see stuff in the middle. We'll see stuff in the counterjet that's pointed away from us. That's the same effect, by the way. Why do you see the jet only going in one direction, not the other? The one coming towards us we see. The one that's going away from us we don't see. So that's because of this Doppler effect. So we think that there's all sorts of stuff hidden in these images. But our current dynamic range, meaning like from the brightest thing we see to the faintest thing we trust, is something like 10. These are not extremely high resolution images. So this is something where we need more sites, we need more sensitivity, and we'll start to see that.
Yeah. I have a question. Will you be able, if the singularities exist, actually resolve it with this telescope system?
Yeah, so we're kind of limited, right? Because everything within this photon sphere, you're not actually seeing the black hole. There's a benefit, right? The light is getting lensed around it, so we see this 5.2 times the Schwarzschild radius. So we see something a little bigger, and it's really tough to see something within that region. Yeah, we're basically trapped. Everything, all the photons that go within that fall inward. So pushing to smaller scales is going to require new ideas, I think.
This is a bit of a different question, but for a project with such unambiguously useful results, how difficult was it to get funding for this type of project?
Well, my wife likes to say the things that inspire us are as important as the things we discover. And I think a really special thing about the project is the things that excite me about it are probably similar to the things that excite lots of you who maybe don't even study astronomy. And I think in a lot of ways we've benefited from that. People, we can't argue that this is crucial to build, self-driving cars or better computers or anything like that. But we are, firmly latched on to this technical development trajectory. And I think that's really helped. We couple this tremendous excitement in astronomy with absolute cutting-edge technology. And that's just been a really potent blend for us. So it's not easy to get funding. It's not even easy to get telescope time. So this morning, about 3 minutes before the deadline, we submitted proposals to try to get more time to observe with the Event Horizon Telescope. So it's always this game. You're always pushing, but we have been fortunate.
Can you use this technology to observe planets?
Unlikely. So there are two things that you have to think about with an interferometer. One is the thing's got to be small enough on the sky that your interferometer doesn't just resolve it out. And the second is that it has to be sufficiently bright. So for us, this black hole that we're seeing in M87, the brightness temperatures you see on these things are like 100 billion degrees. So it's unlikely without some huge technological jump that we would ever be able to see things that aren't glowing with this synchrotron radiation that you see near black holes.
Is the jet from the black hole that's pointing towards us, is that helpful or detrimental to the viewing of the image? Would it be more helpful if it wasn't there, or does it actually help us see it?
That's a great question. If you had asked me 2 years ago, I would have said we have at least 5 years till we can make a picture with the Event Horizon Telescope. And I thought M87 was going to be impossible because I thought we were going to have this big booming jet, and we don't have baselines that sample that very well. So it's really difficult to make a picture of it. It can be obscuring the black hole. There are all sorts of problems it can cause. And there, I think we got pretty lucky, right? At this particular frequency, it doesn't seem like the jet is hurting us very much in the image. But the exciting thing is to push to these higher dynamic range, and then you might be able to see it, right? You might see this faint jet extending, and then you could see the dynamics of how the black hole is actually twisting and powering that jet. But I think that's going to be one of the next major breakthroughs with the EHT is to be able to see, can we see the jet in these images? Yeah.
Just a sociological question. I noticed you've been using M87 to refer to both the galaxy and to the now famous black hole that inhabits it. And I'm wondering if there's prospects that someday in the future, this black hole itself will have a more memorable name.
Wow. Well, you've pointed out one of the deepest sources of division within the collaboration. I am only half joking. We iterated back and forth. Well, it's also funny because a couple hours ago, my wife was looking at my slides. She's like, "Why are you calling it M87? That's the galaxy." And so, yeah, even within my family, I can't. No, it's a problem, right? So it's interesting. In other sources, we have things like Sagittarius A star is the radio source at the center of the Milky Way. But it's not the black hole, it's the radio source. So I mean, I think with discoveries like this, we need new notation, new names to distinguish these objects and treat them more unambiguously. But yeah, it's been a source of tension.
How much will be done on the algorithm side for making the images better? And I'm also curious about some of the details of the algorithm. So you said some image processing stuff. So I'm particularly interested about wavelets and Bayesian updating and probabilistic methods. You said like generating synthetic data and stuff. So it seems like there's a lot of probability and randomness going on.
Absolutely. So we basically have two classes of imaging methods that we use. One of them is this sort of classic method called clean, which is it's a greedy technique where you're basically sprinkling down point sources around your image and trying to come up with a sparse representation of the image. I think wavelets would do much better. The second is basically a Bayesian-inspired method called, we refer to as regularized maximum likelihood. So we basically use probabilistic methods, but then we kind of stretch them in various ways. So we can enforce things like we want the image that's most consistent with the data, but is also smooth. Or we want the thing that's most consistent with the data, but it's also compact. So we basically want to make the most boring image possible that's still consistent with our data. And there are lots of ways of doing this. I want to emphasize, we tried to pick the absolute simplest methods possible for this publication. We didn't want anything to be a stretch. And part of that's because we could, right? We could make images without needing to feed in lots of high-powered machinery. But I mean, I could write for you on the blackboard what the equations that we're minimizing are. They're extremely simple. So I think there are tremendous prospects for enriching these images and enhancing them using algorithms. It's just as you do that, you're feeding in more and more assumptions about what you think the thing looks like. And we really wanted to be able to be surprised if it looked completely different than what our expectations were.
Could you do it in a context-free way? Like you could try to make sure that you're not implicitly biasing what you're showing. Because like I've seen interviews with people who are like, we know we have the real image, it's the data.
Yeah.
Right.
This is a tremendously challenging problem. I would say if you have ideas, we should talk. I think this can be done much better. Yeah.
Oh, this way. Hi. So since it's not the jet since the jet is not very visible in the wavelengths that was recorded, what is the main source of light? Is it just a general like a bath of fluid that the black hole is in, and that the light that's behind it gets lensed so it gets so much brighter on the photon ring, or is it mostly its accretion disk, or what?
Good question. So I should clarify. It might be that what we're seeing is entirely the jet. Okay, it might be that it's entirely the accretion disk. It might be that it's some region where it's hard to even say, is this the jet or the accretion disk? Or it might be that it's both. And that's because when you're that close to a black hole, all that matters is the geometry of the space-time. It overwhelms all of the microphysics that are driving the emission. It overwhelms the specific location that it's lighting up, and it wraps it all around the black hole to produce this ring-like image. So I think where you would see an unambiguous jet has to be away from the black hole. So if we could, that's why if we could push to these scales on larger scales, then we might be able to see the clear signatures of the jet. But at this point, we actually don't know what's lighting up the image.
Hi. Since the light path can curve, how certain are we about the direction?
One more time, sorry.
How certain are we about the direction?
Like the clockwise rotation?
No. The actual direction in the sky.
Oh, well, I mean, the direction in the sky, well, this is an interesting thing. So it turns out you can slide the image on the sky, and that's equivalent to doing a particular change of phase in your measurements in a way that we can't track. So we actually don't have an absolute position on the sky very well. But what we do have is methods of getting the absolute position on the sky of the black hole at slightly longer wavelengths. And this is where they can correct for these phases very accurately. And so we actually know that the black hole is localized to within about the size of this image to the very center of the jet, where you see the jet and the counterjet split. So we do know that it's right at that location. Yeah.
Hey, here. Hi. What is setting the direction of spinning, actually?
The direction of what?
Of spinning. I mean, clockwise or anti-clockwise. What is setting that?
So it turns out that seems to be set entirely by the spin of the black hole. So no matter what the disk is, the black hole, if it's rotating, is going to be rotating the jet funnel wall along with it. So no matter what's lighting up near the black hole, it's reflecting that this black hole has a spin vector that's pointed away from us, so that it's going counterclockwise on the sky. Oh, what caused it to be spinning? Oh, that I don't know. I mean, it could be that it's pulling in lots of material over very long times, and that material has angular momentum that just gradually builds up onto the black hole. Lots of things in astronomy happen like this, and they can get spun up really fast, like pulsars. It could have also gotten spin from mergers with other supermassive black holes in its history. But yeah, we don't have any information to really pin that down.
Is there hope that this technique is going to be able to spot black holes in the Milky Way and other galaxy, and therefore get a sense of how much black holes might account for dark matter?
So I guess there are two answers there. One is M87 is a big black hole in the sky. It's the second biggest in the universe as seen from Earth. The biggest is the black hole in our own galaxy, Sagittarius star. The problem is Sagittarius star is a much smaller black hole. So it's less massive. It's got about 4 million solar masses instead of about 6 or 7 billion solar masses. And for black holes, the time scales are proportional to mass. So a day in the life of M87 is a minute in the life of Sagittarius star. And so where we see just hints of variability on time scales of, say, 5 or 6 days, and where we see this whirling variability where the entire image is evolving on time scales of a few weeks for M87, that's happening on time scales of 30 minutes for Sagittarius star in our galactic center. So we have actually more data on Sagittarius star, and we have another site that's observing because the South Pole can see it. So we even have better data, but it's just a much more challenging problem, and that's why we focused on this first. So that's the first question. The second is whether it's really a component of dark matter. That I don't think the EHT is really going to add a lot to that story. Lots of the candidates for dark matter are much smaller black holes, and these are constrained by other types of measurements like microlensing, where you can see how they affect bright objects behind them. But it's a little hard to imagine that the EHT would accrue such a large sample that we could really contribute to that. And we don't really study the types of black holes that are primary candidates for that. Yeah.
Up here. So I was wondering what effect the accuracy of your atomic clocks have on the resolution of your image.
That's an interesting question. So the clocks, I mean, these are the best masers in the world. And they allow us to coherently integrate our signals for about 30 seconds, or maybe a bit more, maybe a minute. Now, the atmosphere takes over at about 6 seconds for a lot of our sites. So the atmosphere is adding these random delays as different clouds of water vapor are moving through the line of sight. And so what this means is that we're actually being limited not by the accuracy of our clocks, but by these atmospheric distortions that we're peering through. But it's not that big of a difference, right? If we push to really good atmosphere sites, then all of a sudden the masers can actually be the limiting factor, but they're not for the current setup. Yeah.
Oh, hi. I was wondering if you had an idea what Stephen Hawking would have thought with all his thing about whether radiation ever escapes from the black holes, and yeah, if you, no pun, but if it sheds any light on those kind of questions.
Yeah. So I mean, so Stephen Hawking, I think he would have been thrilled at the prospects of studying these black holes on horizon scales. This is where we know that general relativity has to be breaking down. It has a fundamental incompatibility with quantum mechanics in a way that a lot of his work shed a lot of light on. Now, one of his signature predictions was that black holes actually aren't black, that they emit Hawking radiation. So they glow, they can even evaporate, these sorts of things. This is not something that we are likely to test. So big black holes emit almost no Hawking. I mean, I don't know how many orders of magnitude smaller than the signals that we're seeing, but it's many, 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 many. So it's unlikely that we would ever test something like that directly, but I mean, this is right up his alley. So, if Alex is excited, hopefully Hawking would have been too. Yeah.
Is this the best, the highest resolution we can achieve on Earth? Will that, if we add some telescope on the moon or even Mars, can get the higher resolution than this?
Yeah, that's right. So we have two levers, right? One is wavelength. So we can actually keep the same telescopes, but just observe at shorter wavelengths, and that gets us to higher resolution. So one thing that we're doing is we're trying to develop an array at 345 gigahertz, and this would make the images sharper by about 50%. So that's one path, and the problem is that the weather becomes more and more difficult. The second is that we push to longer baselines. So there's already interferometers that operate in space and that actually have baselines going out to the distance of the moon. This is a project called Radio Astron. And so what we're thinking about now is, could we push the Event Horizon Telescope to space? And then you have these orbiters that are sweeping out lots of baseline coverage for you. You can get exquisite images, and you can push to higher and higher sensitivity. So this is something we're working on.
How many more questions can you take?
Well, I mean.
Okay, maybe we'll have one last, two more questions. Let's have two more questions, and then maybe you can stay for a few more minutes if
Absolutely, I'm happy to talk.
Want to come down and ask you one-on-one?
Well, actually, my question just probably going to answer that just now. But I mean, in terms of increasing the angular resolution, can we do more on this algorithm side as well?
Yeah, so there's this nominal diffraction limit that's lambda over d. We find that we can pretty confidently push down to about half that using algorithms. You can push down to a quarter of it, but then you have to start feeding in pretty tight assumptions. Like if we said we know that the black hole looks something like these numerical simulations, we could create sharper images that would probably be pretty good. But it's really hard to remain agnostic and push down below about half that limit. If you have ideas, it's always possible that some new breakthrough will change that. Yeah.
Does the direction of the spin or of the jets have any impact on the intensity of the image or how well we're able to see it?
Absolutely. So it turns out that as you rotate the black hole, it can change the appearance of the image quite a lot. And so instead of, for instance, if you tilt it and you're looking at it edge on, then the shadow doesn't look like a circle anymore. It flattens out a little bit on one side. And so that might be a way to look and see if the black hole in the center of our galaxy is spinning. And that would also change the brightness. So yeah, absolutely, the spin can have a big effect on the image. It just happens that because we see this big booming jet in M87, that's why we think the spin is probably pointed almost straight at us. Yeah.
Okay, well, this was an amazing presentation and an incredible success. So let's give the EHT a round of applause and thank Michael.